Hey, welcome. This video is going to be about the chapter 3. First, I'm going to go over the basic vocabulary and concepts of the chapter. So this is pretty much straight out of the book. So let's go on. All right, the first main concept of this chapter is the idea of triadic closure. That is, that if we ever have two nodes in a network with edges to the same node, so for example, if we have A and B and C, and so if A has a node to B and A has a node to C, there's an increased likelihood that we're going to have nodes B and C are going to have edges to each other at a future time point. So this is part of our idea of predicting what will happen in the network. And for me, I like to call these a source of tension. That is, the A, B, and AC relationship is a source of tension that B and C should somehow have some sort of relationship. The book emphasizes a lot the friendship network mechanisms. That is, opportunity, meaning in this situation, A, B, and C, that B and C are going to be more likely to meet each other. The trust idea is that since A and B have a relationship, or I guess both B and C have relationships with A, that they're more likely to trust that, B would trust that C is a good person, C would trust that B is a good person, and then they would form a relationship also. The final one of incentive is that, if A and B are going to parties together, A and C are going to parties together, eventually it just makes more sense for A to sort of have B and C, everyone go into parties. Hopefully you can see here that we can have a situation where maybe, B and C don't get along. And so that's why I'm saying this is like a source of tension in the network. And again, there's multiple reasons for why this would happen. These reasons in the book are for a friendship network, and I want to emphasize that there's other types of networks we have here, a supply chain network, trade networks, other things like that. That there's different mechanisms at play here. When that comes up, we'll discuss it. It's probably later in the thing. The final point about triadic closure is that as triadic closure occurs, the clustering increases. So as we add that B and C link, that becomes a cluster. So let's talk cluster for a second. The clustering coefficient is sort of the density of a cluster, and that is just defined pretty simply as a proportion of total possible edges that are currently edges in a network. So we got two diagrams here. So I got diagram A. If we're talking about A here, the proportion of possible friend edges for A, you notice we got A is related to C, D, or B, C, D, and E, and really only C and D are connected. But over time, we can see that there's some new edges forming. There's one between B and C and one between E and D. And that means that the clustering coefficient is increasing. I'm not going to give you the definition right now because I actually want to walk you through it, and we'll do that later because it's not exactly clear how the book was getting after it. But again, here, the idea is we're creating, or there's becoming a cluster here where all of the nodes are connected together and they're not sort of connected separately. All right, next up, edge characteristics. So just generally speaking, edge before has been a connection, and we've got, this is the structural sort of definitions of edges. We've seen these actually in the previous chapter, which is the what the gatekeeper was, and a local gatekeeper or a pivotal node. For an edge, these actually make a lot more sense. With an edge, an edge that we'll call a bridge is on a path between two nodes that if you remove that edge, it divides the graph into two components. Okay, so a bridge is like the gatekeeper in the previous chapter, meaning, remember if we took out the gatekeeper before, the graph is separated into two components. Here, we're just talking about an edge, and this actually makes more sense. I mean, sure, it is true that, we have friendship networks, etc. If a friend dies, that would be the most drastic reason why a graph would fall into two components. Like a friend that, or someone that's at a bridge position dies, then yeah, you've divided the graph into two components. This edge removal is something that would happen a lot more often. So bridge divides into the whole graph into two components. A local bridge, this is what you see more often, where the edge is on a path between nodes, and if you remove that edge, it's going to increase the distance between those nodes. So, you know, we had the A-B-A-C stuff before, and if we popped out one of those links, you know, the A to B link, now the distance from A to B is no longer 1, it's, you know, 2. So local bridge is, yeah. Right, so what's our point here now? Edges are maintained by nodes. So what when we were talking about gatekeepers before, a gatekeeper is the one or ones that maintain a bridge. The pivotal node is the one that maintains the local bridge. So if you look in this diagram, in the book they oftentimes will leave off G, and then they would say, you know, here we've got A and B. If that edge is removed, you know, you'd sort of divide it into larger or two components. In this, just as it's drawn here, if A and B edge is removed, you know, distances immediately increase. You know, we can see right now, if we go from C to say H, that's a 1, 2, 3 hop over to H right now. If we take out the A to B edge, now we have to go, you know, C, F, G, H. Oh, that is still 1, 2, 3. Well, there's more down in there. If you go to the ones that are directly connected to B, it would be a lot more on the bottom right side. So taking out edges, and when it increases the distance, then we are saying that's a local bridge. Right, next up in the chapter is the strength of an edge. And I want to emphasize that some of this stuff about edges is all about the definitions of the researcher. When we talk about strength of an edge, the definition of the researcher is super, super, super important, okay? And it will get worse when we get into the next chapters about especially negative and positive relationships. That's sometimes pretty rough to model. Here, we need to understand, you know, strength of an edge, we've got to say, you know, what makes it strong? These three I'm showing here are probably the three really good ones in terms of strength. Strong tie would be greater frequency. In the book, yes, they do a strong tie as being like greater length of use. So greater, like if you talk to someone on the phone for a longer period of time. That was another strong tie. I probably ought to add that here, huh? So greater frequency is a strong tie. Low frequency is a weak tie. Friendship we're used to. Who are you friends with? And who are you acquainted with? We got to keep in mind here, there is also a definition of that too. You know, friendship might be something as simple as, have you ever had drinks at their house? Acquaintance might be, you've had drinks with them, but not necessarily at their house. So there's, it's always a definition to these edges, and we got to be specific about what we're talking about. The last category here, the more or less dependency. This we'll kind of get into, but you know, it's more of the like, I like this edge, I need to use the edge. If it's gone, I'm kind of hurting, and a weak tie would be less dependency. So there's, yeah, when we're talking about strong and weak ties, it's definitely a definitional thing, and you got to remember that. This is also, by the way, sort of in combination with the previous stuff about bridges and the local bridges. That is, you know, you might have a network diagram of just the weak ties that would be much more connected. And if we graph just the strong ties separately, you know, that might have multiple separate components in it. And we'll worry about that later, I guess. All right, strong triadic closure property. So this is with the idea of a strength of an edge. the strong links here, or the strong edges, are the ones that are in play. Okay? So what we're saying with strong triadic closure in sort of plain English is that triadic closure is going to be even more likely when strong ties link to the same node. So earlier we talked about A, B, and C, where A was connected to B, A was connected to C, therefore it's more likely that B is going to connect to C. If we fold over the strong ties onto there and we say, A and B have a strong tie, A and C have a strong tie, the strong triadic closure property says it's a very high probability that at least a weak tie will form. It might happen that a strong tie will form. So this is just a sort of a quantitative way of characterizing the link that would form, or quantifying the tension in the network. Okay. This also notes here, if there's only weak ties to the same node, then it's less likely to have any triadic closure at all. So it's sort of the probability of triadic closure increases with the strength of the edges that exist. Okay. So what follows from this whole argument is that local bridges are therefore much more likely to be weak ties than strong ties. And we'll illustrate that right here. So this is the diagram from the book where they've taken that earlier one and they've mapped it out and said basically, what combination of strong and weak ties would work here. Hopefully, well, let's not say hopefully, you are going to look at the diagram now and you're going to see this link between A and B. That's that local bridge, and I guess I was saying here, yeah, we're worried about the C route over to what's below B, those unlabeled circles. If we take out the edge between A and B, that local bridge, it increases the distance there. So why is that going to be, or why should that be, a weak tie? If you look at it and you said, oh, wait, what if it was a strong tie between A and B? Well, if we have a strong tie between A and B, what follows from strong triadic closure is that B and E should have a relationship, B and D should have a relationship, and B and C should have a relationship. Since they don't, that's why we're saying here it's probably going to be a weak tie. Okay, and so that's, it's just a given. And it's because the stronger that tie gets, the more tension there gets to be in the network. So just thinking about me, so my personal situation here is I have a lot of strong ties to people here in the United States. I have ties, and maybe you would characterize them as strong ties with people in Germany, but honestly speaking, they're probably not. Because these ties to the people I know in Germany aren't, in a lot of cases, they aren't strong enough that I have connections to their friends. So there's not going to be clustering of me to others, sort of in Germany, because, that's friend of a friend, the way it is in the United States for me right now. So in a way, I'm more like A here with all the strong ties, and then the people in Germany that I know are kind of more like the Bs, where they have their own friends, the people they see all the time, and, just structurally speaking and tension-wise, it starts to cause problems, actually, in a network. Not problems, I guess, but it would cause even more links to form. I've heard from other students that they think of things like, if we look down here at this DE link and it says weak, and over on the B side there's a weak link over there. What's happened is that the authors of this book are trying to put the necessary number of strong ties in, and if they can get away with a weak tie, they'll put it in. So, this E and D, it could just as easily be a strong tie. It doesn't violate any property. But by being a weak tie, it doesn't violate the property either. But notice that A to F and C to F, that has to be weak. If that was a strong tie, then F would need to be related to other people, D and E, and they're not. So, that's what's going on there. So again, we're comparing, if we go back to this other diagram where the links weren't labeled strong and weak, this would be kind of what they would look like. Yeah. All right, clustering coefficient. I promised to show this calculation. And again, it's a probability that two randomly selected nodes that have an edge with A will also have an edge with each other. So if we're looking at, the clustering around one node in our network, we're trying to say, what is the probability that sort of the nodes around A are clustering together? You start with this by, of course, mapping the network just as it is. This is the initial network value that we had before. And here we have, this is A. If we look at A here, A has reported in some way edges to B, C, D, and E. Of those, only C and D have a relationship. Now, where do we get these 6 possible edges here? There's actually 6 possible combinations. It's going to be B to C, B to D, B to E, that's 3. It's going to be C to D, C to E, that's 2. And then it's going to be D to E, that's 1. This is where we get that 4 plus 3 plus 2 plus 1. And you hopefully did this in the homework, and it's actually pretty straightforward once you start doing it. So there's A with the initial set being a clustering coefficient of 1 out of 6. As time evolves, over time people communicate more with each other, etc. Friend links form, etc. We have a newer network, and here we have B and C connected and D and E connected. Notice that connecting D to G has no effect on A's clustering coefficient, because the clustering coefficient of A is related only to who A is directly connected to. So clustering coefficient now goes up. Now we have 3 possible links out of the 6 possible edges present. And so again, A's clustering coefficient has gone up. There's a pretty significant amount of research on this. If you look at people's clustering coefficients sort of in daily life, the people with a higher clustering coefficient tend to be sort of happier and less likely to have things like depression and other stuff like that. So clustering is actually kind of a big deal in terms of people's mental well-being. All right, there are some things that need emphasizing from this chapter, as always. Again, this book is written by economists. We are more about sort of sociology, social psychology, business stuff. And so we have a few things that we need to get into. All right, next thing. This is not so obvious in the book. They do a cell phone data set, and they kind of go through it, and they don't really explain what's going on. What the point you need to get out of that whole exercise about the cell phone data is you have an enormous set of real-world data. What they're doing with the whole thing about strong and weak ties is they're actually trying to validate the measure of it. So they're trying to say that the number of minutes you call someone over the time period is the tie strength. So, if you talk to grandma 90 minutes over the time period and you talk to the barber 5 minutes, grandma is a strong tie, barber is a weak tie. They're trying to validate it, and they're validating it using that neighborhood overlap as a measure. And so keep in mind what you would be doing here as a researcher is you're going to go through this huge set of data. It's massive. And you're going to validate it and say, look, given this cell phone data, we assert as a researcher that the total number of minutes is a measure of the tie strength. And the way we're going to do it is we're going to say, okay, who in this network has less what they call neighborhood overlap. And we'll talk about that actually some more in a second. But the idea is to find the local bridges in the network. Once we find the local bridges in the network, that means these are nodes in the network or edges in the network that are only sort of transient and that they link to other clusters in the network. So they're validating it as, we got a weak tie. That's very much more likely to be one of these things with a low total number of minutes. Now, the conclusion, and this is important really from the book, when you get these really enormous data sets, they're super, super complicated, and you can't break it out like we've been drawing here. So I'm drawing here on these diagrams, 9 node, 10 node, 12 node, maybe a 20 node network. With those, you can sort of break it out and show, there's a little cluster here, a little cluster there. But in a normal network, you just can't look at it like that. It's too big, and you have to have these quantified measures. All right, next issue. This has to do with those quantified measures. This is a fairly large data set, but here, the Facebook data set that they're showing you, if you actually look at just one person, you can visualize it. And so what they're doing here is they had 4 different sort of sets of, and they basically call them tie strength. The main sort of weakest tie would be the friend, everyone on someone's friends list. And they're going to go into the Facebook data set, and here's all the friends that you're connected to. And given the one person's friends, so that very center person on the node, they then cluster them into, who among those friends is also friends with each other. We don't have a calculated coefficient because we're visualizing it, but hopefully you can see here in the all friends network, there's the top section that's definitely a cluster, very tight-knit cluster. The right section is a pretty tight-knit cluster. And then over to the left and around to the bottom, you can see that the clustering sort of just fades away. So that's the weakest ties in the network, and they're sort of overlaid there. Then we have this maintained relationships, and this is people clicking on things in their news feed, and that shows, in terms of just clicking on things, that the person following, this person at the center of the network, is clicking on things in this one cluster, that upper cluster, more so than they click on things in that right cluster. You can also see, this is what they're trying to say here is, that right cluster is probably people that knew each other in the past. And if you see in the maintained relationships, there are people in the present that are still connected in that cluster. But given this one person is the focal structure, they don't really pay that much attention to those people. All right, so we got maintained relationship. That would be like the next, what they're arguing is the next strength of relationship. One-way communication, that is someone has sent a message to someone, and then mutual communication, they got a reply back. So the idea here is, we're escalating the strength of relationships. I would argue here actually, once you get to mutual communication, that they've kind of messed up the time period, or really in a way, the one-way communication and maintained relationships are more or less the same thing. And mutual communication is just, and most people's communication doesn't even happen on Facebook. To me, that mutual communication diagram kind of shows you how bad Facebook messaging is, I suppose, or at least it was at the time. I guess that's the final point on Facebook things. What they were showing, the researchers wanted to show that people do maintain a huge friend circle, but they're using what we'd call atypical communication. They aren't actually communicating with each other, so there's not two-way communication. They're just clicking on links, maybe liking and sharing. I think that was what maintained relationships was. Yeah. All right, next topic. This isn't hit hard enough in the book for me, and this is the idea of embeddedness. Okay. So embeddedness is actually, if you go back up to the cell phone data, embeddedness was one of the measures they were using to see if people were sort of properly neighbors to each other. So embeddedness measure here is if you take an edge, how many common neighbor edges does it have? So if you look at the link between A and B, it has an embeddedness of 2 because A and B, there's also links from A to E and from A to F, and from B to E and from B to F. So there's a full set there that they are, there's edges right there. So A to B is an edge. Of the things connected to A and B, there are 2 that are sort of fully connected to both. So A and B has an embeddedness of 2, that's the E and F relationship. And then if you look at B to D, the embeddedness there is 0. And that's how we get the idea that that is a local bridge. And that's the idea of it's probably a weak tie because hasn't been any triadic closure. The further thing on embeddedness is the idea that being a local bridge, so B to D, it has advantages and disadvantages to the people maintaining the link. Okay? So the link from A to B, that has advantages in terms of, A and B are maintaining that link. They also both have relationships with E and F. And so those links sort of build to each other. It might be easier to maintain that link. They might get benefits out of it, get to go out to drinks more often, hang out with each other more often. And so there's being highly embedded. I guess we already talked about that already with the clustering coefficient. That means you get social advantages. Low embeddedness does have its own advantages. One of them especially is this idea of the monopoly of information and resources. That is, by maintaining the link from B to D, B has access to things that the people A, E, and F don't have access to. So B can use that link, maintain that link to get certain advantages, resources, and other things. In addition, the book brings up this exposure to outside threats. That's a negative thing, right? So B and D having this edge means that where B and D they're kind of separated. They're on these separate nodes, they're on separate clusters. But D is more exposed than, say, A would be. And I guess ironically here, exposure to outside threats in terms of, I don't know, what we would, if something really gets threatening, like say the AEF, like these people have a big fight, I would actually say that B has more insurance by maintaining the links from C to B, or to C and to D, because if something happens crazy, they can get back on it. This whole embeddedness idea has a big sort of idea or linkage with the ideas of social capital, and that is in social capital, the idea for people is if you have a lot of social capital, you can bring your social network resources to bear. If you're highly embedded, that is like the A and B. So A is super highly embedded, the A and B link is quite embedded there, and they have a sort of a bonding link there. That is E, F, B, and whoever else they're connected to. They're sort of on their same team, and that's the idea of bonding and bridging. That is, A is sort of there helping stuff work. The links on the outside with low embeddedness is a different kind of social capital, and usually they call that the idea of closure or brokerage. That is, or no, they actually don't. That's the brokerage one. Sorry, I mixed them up. Brokerage is one of the edges, and bridging is also the edges one. It's closure and bonding is what the A would have. So brokerage here is like, B can offer these resources to this other cluster that's A, E, and F that A doesn't have access to. That's brokerage. It's also bridging. Sorry, I confused that a little bit. And then, like I said, A is bonding, and A has the closure idea. So embeddedness is sort of one good reason to maintain edges.